All right. Now, projection tensors have certain properties, and we will look at them now. Okay. Okay. The properties are the following. So any projection tensor P, right, I'm not going to write it as P sub T or P sub N, right? I'm just going to write it as P, right? It could be either P sub T or P sub N. So what we have is that P acting on P gives you back P. Okay? This property is what we call idempotence. All right? So this implies then that P sub T acting on P sub T gives you back P sub T. What this means is that if we now multiply this on the right by U, okay, that's what we get. If we project U along the vector T and then try to project it again along T, it does not change. Okay? All right? Right? So this is the effect of projecting U along T once and then trying to project it again. Well, any projection after the first one makes no difference. Okay? The same thing with N. Right? So if we take Pn acting on U, that's the same as Pn acting on U. Okay? But now, what if you try to do something different? What if you try to do P sub N, okay, acting on P sub T? Okay, let's test it by making it act on U. Okay, what you will see is that this is the zero vector, always. Okay, what this implies is that P sub T is an orthogonal projection relative to P sub T. That's easy enough to check. Okay, so let's check this quickly. Okay. Okay, let's start out with P sub T acting on U. We know that this is U dot T along the T direction. Okay, but then P sub N acting on P sub T of U is equal to P sub N acting on U dot T T. Okay. Now U dot T is just a scalar, right? So it comes out of this calculation. So this is U dot T times P sub N acting on T. Okay. Now P sub N acting on T, we know is U dot T comes along for the ride. P sub N acting on T, we know is our identity acting on T minus P sub T acting on T. Okay? If I continue here, remember this is the calculation I'm trying to do. Okay, this is U dotted with T acting on, multiplying identity times T minus P sub T acting on T. I'm writing this out in great detail. You probably already see this final result. So, identity acting on T is T. How does P sub T act upon T? Okay, it is T tensor T acting on T, okay, right, which is U dot T times T minus, all right, now here we get T dot T, but T is a unit vector. So that's going to give us 1, leaving us finally with T times T dot T. But since T dot T itself is equal to 1, we see that all of this reduces to 0. Okay? So these projection tensors Pt and Pn are perpendicular to each other. We will find great use for them as we get into the definition of our constitutive relations. The very last thing I want to touch upon in this segment is a fairly short one. It's a fairly short subtopic, and it's something that is almost certainly already known to all of you. It is the idea of symmetric and skew symmetric tensors, right? Okay, so A and B, as before, are tensors. Okay, then A is symmetric if A transpose equals A, right? In coordinates, what this means is that A ji equals A ij. Okay? If we write it out as a matrix notation, right? We use matrix notation for representing our tensor. What we have is the following, right? We have A11, A12, A13, A22, and here we would have A21, but because of the symmetry, we have A12 there, right? A21 is essentially the same as A12. So we have A23. Here we would have A31, but it turns out to be the same as A13. Here we would have A32. It's the same as A23, right? And here we have A33. Okay? Now, the other tensor B may be skew symmetric. Okay, and it is skew symmetric if B transpose is minus B. In coordinates, we would write that out as B ji equals minus B ij. In matrix notation, okay, we would have the following. Now, in matrix notation, or actually even in coordinate notation, what does happen with the diagonal components of a skew-symmetric tensor? Think about that. Chances are you all already know the answer. The answer is given by just looking at this and asking yourself, what happens if j equals I? Okay, if j equals I, we have things like bii equals minus bii, but that's possible only if that component is 0, right? So the diagonal components of a skew-symmetric tensor are 0, right? And the off-diagonal components are negatives of one another. So we can have b12, b13, b23, minus b12, minus b13, and minus b23. Okay? One great use of this representation of symmetric and skew-symmetric tensors is the following, right? So any tensor C, right? So if C is another member of the space of tensors, the space GL3, right? Okay, so any tensor C can be written as the sum of a symmetric and a skew-symmetric tensor. Okay, how do we do that? Example, define A as 1/2 C plus C transpose, and define B as 1/2 C minus C transpose. It's easy enough to check that A is indeed symmetric, B is skew-symmetric. Okay? So this guy is symmetric. And this is skew-symmetric. Okay? And clearly, if you add A and B, you get back C. Right? And we can clearly see that C equals A plus B. Okay, so this is a very useful representation of any general tensor that we will often use as we go ahead with the rest of continuum mechanics. Okay, we're going to stop here for this segment.